Hello and welcome back to the channel, to the video series where we are reviewing the principles and practices of commercial construction textbook. This video is about chapter 10, and that is all about structural timber frame. As we already know, timber as a building frame material has been used successfully in many forms throughout the world. So it's one of the most versatile materials used in the construction industry because of its relatively lightweight, and it has good tension and compression strength, and it's very durable when protected from decay and insects. So timber is used for pile foundations, beams, columns, bracing, and trusses. And many of old wood frame buildings are still in good structural condition and are being used today. Original buildings made with a heavy timber frame were structures of two or more stories intended primarily for industrial and storage purposes. Heavy timber framing has now been expanded from the original industrial purpose to include schools, churches, auditoriums, gymnasiums, apartment buildings, supermarkets, and so on. The production of modern type of timber connectors has made it possible to develop the full strength of wood when stresses are being transferred from one member to another. It's no longer necessary to provide much larger sections to accommodate the fastenings formerly used to transfer stresses from member to member. The most significant development in the timber industry is the production of heavy timber sections by glue laminating and production of structural sections using random length veneers and strips. Heavy timber construction implies that the section sizes used in the frame are of sufficient size to provide the necessary degree of fire resistance required by local fire codes. So let's move to the next subsection, and that is the structural frame. Structural frame is an interrelated arrangement of load-bearing sections that, when put under the influence of external loads, will ensure the structural integrity of the building. So the structural members must be capable of resisting the stresses imposed on them without showing signs of failure or without producing failure in related members of the frame. In the design of a structural frame, the objective of the structural engineer is to provide an economical structure using the appropriate materials without compromising the performance of the frame. Performance of the frame is its ability to support loads without exceeding specific deflection limits. Non-structural elements depend on the structural frame for support. So glass panels, masonry partitions, and drywall ceilings are typical non-structural elements that require fairly stringent deflection limits to ensure that they do not become overstressed by excessive deflections. Deflections on floor beams are also dictated by the need of the occupants to feel comfortable within the building. So structural frames can be classified as braced frames and unbraced frames. A frame can be defined as a braced frame when lateral displacement has been prevented and any lateral movement that occurs is small. In a braced frame, the connections between the structural members are normally designed to resist gravity loads. Cross bracing or other structural components such as shear walls, stairwells, and elevator shafts are used to provide lateral stability to the frame. In an unbraced frame, lateral stability is developed through the rigidity of the frame members and the ability of the connections to resist rotation. So wood frames that have large open areas, such as gymnasiums and hangars, depend primarily on the diaphragm action of the wall sheathing and roof decking to transfer lateral loads into the foundation. Diaphragm action is developed by nailing plywood sheathing or plank decking to the frame. And please refer to the images. You can see how masonry walls provide lateral stability for timber frame structure. And also you can see the diagonal decking that adds rigidity to structural frame. Basic components of structural timber frame buildings may be classified as columns, beam, purlins, trusses. The connectors that are required for them are decking or planking. The size of each used in any specific case will depend on the load and the span of girders, beams, and planks. The unsupported height of columns and the species and grades of timber being used. So please refer back to the textbook and you can see the chart with the sizes of sawn timber sections, and you know already that nominal size is different from the actual size. So for example, 2x4 is 1.5 by 3.5 inches, and so on. So please refer to the chart. So let's move to the next subsection, and that is timber connectors. So there are various types of connections that have been developed for the joining of members in the timber frame, and also for the anchoring of the timber frame to its supporting foundation. So please refer to the image. You can see the typical timber connectors, and those are bolts, lag bolts, straps, T-straps, U-strap, angle, masonry connector, base plate, saddle, and hanger. Glulam and timber rivets are special heavy-duty nails that made of high-strength steel for use in glue laminated member connections and other timber connections. Many codes limit the use of these rivets to Douglas fir sections only. Glulam rivets are used in conjunction with pre-punched steel side plates to achieve load transfer from one section to another. Also, take a look at the image. You can see the shear plates, and those are intended to prevent the deformation of the timber due to the forces in the bolt by distributing the forces over a much larger area of wood. They can be used for steel to wood or wood to wood connections. So you can see the pressed steel and malleable iron. Split ring connectors use the same principle as do shear plates, except that the bolt is not used in the transfer of load from one member to another. The load is passed from one member into the split ring and into the other member. And please take a look. There are images and pictures showing that and showing the sections as well. Nails are used extensively in light truss construction, light framing, application of sheathing and decking, formwork, built-up beams, and stressed skin panels. The capacity of a nailed connection is based on the lateral resistance developed by the nail when driven into the side grain of the wood section. The nail capacity depends on the nail type, whether it's smooth or spiral, coating, length, and the species of wood being nailed. Truss plates, so those are used in the manufacture of trusses, and this type of connector replaces the need for gusset plates and provides a quick method for connecting the web members to the cord sections. The plates are pressed into the section of the truss to be connected using a portable hydraulic press, and there are various sizes and types, so please review the images here. We are moving to the next subsection, that is the wood columns. So that is a structural timber frame element and a normally solid sawn timber or glue laminated sections. You can see typical column splices. You can see wood splice plate that has the bolts and the washers, and you can see the metal strap as well as the dowel. Column to base connections. So the first consideration is erecting a structural timber frame is the method to be employed in anchoring the columns to the foundation. This may be done in several ways. For example, take a look here at the shear plates that are set into the column behind the straps. This may be done in any of the connections when conditions require them. So again, please take a look at the image. You can see typical wood to column, wood column to base connections. There are a few of them. So it can be with the base plate and glue-lam rivets. It can be just with the angle and the base plate. Also, it can be base plate with a U-strap that's attached to the pier, and that can be with the anchor bolt and the concrete pedestal where there is a base plate and the strap. Also, we can find metal straps with bolts and shear plates that are attached to the bearing plate, and that is connected to the foundation by the anchor bolts. Stud walls. Structural components used in a timber frame do not always consist of heavy timber sections. Wall framing consisting of vertical sections of studs spaced 12 to 24 inches on center and nailed top and bottom to horizontal plates is a very common method of wall framing. Studs and plates normally consist of sawn lumber having a nominal thickness of 2 inches and a nominal depth of 4 to 6 inches. That's for the most part the residential construction. Exterior walls may be load-bearing or serve as secondary framing between load-bearing columns and beams. When used as secondary framing between columns and beams, the stud wall framing must be robust enough to resist horizontal loads due to wind normal to the plane of the wall. Exterior load-bearing walls that support gravity loads may be required to resist horizontal shear loads in the plane of the wall, as well as bending that is normal to the plane of the wall due to wind loads. For wind uplift considerations, wood connections must be capable of withstanding tension from uplift loads. For this reason, there must be continuous tensile load with the foundation through the roof. To achieve this with wood, it's necessary to provide galvanized metal straps to connect the wood to other elements to maintain the tensile load path. In general, these are straight metal straps with pre-punched holes for nails rated for the amount of tensile load expected for the particular application. We are moving to the next subsection, and that is wood beams. Beams used in a timber frame are either simple span or are extended over the column in what is known as cantilever construction. In cantilever construction, the beams pass over the top of the column a short distance, and then the remaining gap between the two cantilevers is filled in with a short, simple span section. In case of simple beams, the beams span from one column to another and may rest on top of the column or may be connected to the sides of the column. So again, please refer to the images. You can see typical continuous beam to column connections. And you can see that is done with the shear plate and strap connector. That can be done with the connector pins and pipe dowel. And that can be done with the pipe column that is supporting the continuous beam with a U-shaped column cap. That can be done with a bearing plate with a strap connector and the angle connector on top of the continuous beam. Also, it can be a plate connector that is welded to the U cap, as well as the T-strap connector that connects the column and the continuous beam. So what also is important to see here in this subchapter is the beam to masonry wall connections. So buildings may be designed with masonry exterior walls and a structured timber floor and roof frame. In such cases, the framing members must be connected to the masonry wall or to pilasters built into it. Please refer again to beautiful images here. You can see typical beam to masonry wall connections, and you can see that the beam is connected to the concrete wall by the bearing plate, or you can see the bearing plate beam, beam size only, and also glulam rivets that are welded to the bearing plate that is sitting on the brick wall. Another connection is between the beam and pilaster with the anchor bolt and anchor pins that is sitting on the bearing plate. Also, they can be a curved or pitched beam that is sitting on the wall with a slotted hole connector. Roof beams. The method used to connect roof beams to exterior masonry walls depends on whether there is a parapet extending above the roof or if the rooftop is a flush deck, which covers the top of the wall. In case of a flush deck, a fascia is required along the top outside edge of the wall to provide solid backing for the roof flashing. When a party wall or firewall is involved in structural timber framing, the framing members tie into it from both sides. And you can see the roof beam connections to masonry wall. Again, refer to the images. You can see, and it's definitely worth seeing than just hearing about that in the video or somewhere, just if that's the audio part of it. When we talk about intermediate beams and purlins, in many timber designs, smaller intermediate beams and frames into the main ones are framed into the main ones at right angles to them. And it's to these that the design decking is fastened. In case of the roof, purlins may span from beam to beam and carry the roof deck. These smaller members may be carried on top of the main beams, supported on ledgers fastened to the side of the beams. Um, so other designs will call for the decking to be applied directly to the main beams. And you can see the pictures showing intermediate beams framed with hangers and intermediate beam supports. So the next subsection is floor and roof decks. So timber floor and roof decks can be constructed of plank decking or laminated decking. Plank decking is used in most applications where extreme weather of the exposed surface is not a concern, and laminated decking is used for bridge decks, loading ramps, and warehouse floors where high wear is anticipated. Plank decking is a tongue and groove material that is laid on the wide side over supporting members. Plank decking is normally available in three thicknesses: 2, 3, and 4 inches. That's the nominal size. The 2-inch decking has a single tongue and groove, while the 3 and 4-inch thicknesses have a double tongue and groove. And please, again, you can see types of plank decking here in the images. You can see the single and the double tongue and groove system. Laminated decking is usually 2-inch thick nominal material that can vary in width from 4 to 12-inch nominal. And again, I remind you that nominal and actual sizes are different. So please pay attention to that. Laminated decking is placed on edge over supporting members and spiked into place to provide a load carrying surface. Take a look here, the laminated timber decking section. So, three basic patterns are used for laying decking: simple span, two span continuous, and controlled random spliced. You can see that here in the images, deck laying patterns. And we are moving to the next subsection, and that's the glue laminated timber or glue lam. Bonding wood with adhesives is quite an old art. Examples of it have been found in Egyptian tombs. It was used in Europe for construction purposes as early as the 20th century, where it gained needy acceptance, but not until the early 1930s was glue laminated structural timber introduced in the US. World War II and its heavy demand for military and industrial construction provided the impetus that made glue laminated construction commercially important. As far as the materials used, glue laminated timbers are widely recognized as being among the finest permanent structural materials. They're made from kiln dried stock, mostly Douglas fir and southern pine, with some western larch and western hemlock. Both fir and pine are extremely strong, straight-grained, tough, resilient, and durable woods. The larch and hemlock are not quite as strong but match the fir and pine closely in color and texture and are used in areas of the laminated beam where flexural stresses are less of a concern. Um, the manufacture of glue lam begins with the selection and grading of the laminating timber. The finished product will be only as good as the pieces that went into it, so the laminating stock must be of good quality. The lower grade of laminating stock are almost equivalent to select structural construction and standard grades of joists and planks with special edition limitations that qualify them for laminating purposes. One of these limitations relates to cross grain. Limitations in this aspect of material selection are more severe than those commonly imposed by grading rules. So please see the chart here. You can see the strength ratios corresponding to slope of grain. And you can see the maximum strength ratio, which shows the fiber stress in bending or tension and stress in compression parallel to grain. You don't have to memorize it, but that's something that you should know where to find. Uh, Preparation of material. So the laminated stock must be dried to a moisture content as close as practicable to what it will attain in service. It must, in any case, not be less than 7% or more than 16%. And there are two reasons for these limits. One is to provide the moisture conditions under which the best possible glue bonds may be obtained. And the other one is to ensure that there will be as little dimensional change as possible once the member has been placed in service. So take a look, you can see the lab where the person is measuring moisture content of laminated stock with electric moisture meter. Here you can see the another set of images, and you can see the end joints for laminating stock. It can include plain scarf joint, stepped scarf joint, butt joint, and finger joint as well. Every piece comprising a single lamination must be of equal thickness to avoid gaps in the glue lines, which will affect strength. For practical reasons, laminating plants maintain a constant thickness of all laminating stock. The standard thicknesses used by most manufacturers are 3/4 and 1/2 inch, with a permissible tolerance of 0.0075 inches. You can see another image, checking a person checking thickness of laminated stock with a go no go gauge as it comes from surfacer. Assembly of material. The first step in the assembly of a glue lamp is the positioning and gluing of end joints. This must be done in such a way that the completed joint after bonding will be the same thickness as the lamination. End jointing may be a separate operation, but many manufacturers have devised systems of indexing scarf joints for gluing during the assembly operation. One is to bore a small hole at the time the scarf is made so that a dowel can be inserted during assembly to hold the two pieces in the right position. When used, the stepped scarf helps to position the two pieces at a joint. Other methods of making meeting joints automatically, including hand pinning, are also employed. Finger joints do not secure indexing prior to assembly. So the laminations are coated with adhesive by passing them through a mechanical glue spreader that controls the amount of adhesive applied. Scarf joints are coated and pinned during this operation when the single operation assembly system is used. Finger joints are sprayed with adhesive, filled together, and set electronically in a single operation. And you can see there's a picture of the factory. You can see the assembly line of a large glue lamp beam. Clamping begins as soon as the final laminations have been placed in the jig. Steel bolts with wood or metal clamp blocks are commonly used to press the laminations together. Clamping begins at the middle and progresses toward the end, tightening the nuts with an impact wrench set to produce a pressure. And again, please refer to the images. You can see how it's done in the factory setting. Properties of the glue laminated sections. Uh, Nominal sizes are not used in the metric system, so all member sizes are designated by their actual dimensions in Canada. So the lamination width greater than 10 3/4 inches or 275 millimeters are composed of two boards with joints staggered in successive layers. The American Institute of Timber Construction, or AITC, uses similar standards for dimensioning. However, the AITC uses nominal dimensioning for its sections, with laminated sections composed of nominal 1 inch thick sections with actual thickness of 3/4 of an inch. Please refer to the chart here. You can see nominal and finished width. And also you can see the edge joints staggered here. So glue lamp sections are wrapped with a protective paper covering that should be left wrapped as long as possible. Ideally, it's recommended that the wrapping be left in place until just before the glue lamp sections are permanently protected from the weather. If the sections must be stored on site for any interval of time, blocking must be provided to keep them off the ground, and spacers are recommended between stacked sections. So let's take a look at the types of units. Glue lamp members may be used independently or in conjunction with other materials in the construction of structural units. For example, trusses may be built with glue lamp cords and sawn timber webs, using such as folded plates or other stressed skin panels may be combinations of glulam, timber, and plywood. And you can refer to the section and see it here. There are images and graphics here. There are a few basic types of beams that are made, and those shapes are straight, tapered, symmetrically tapered, and curved. So you can see images here, and also the three hinged arch most commonly used for the heavy timber application, and glulam may have legs that are straight, circular, or of varying curvature. Straight-legged arches are normally either high V or low V, and the V arch allows maximum utilization of enclosed space. So please take a look at the arch shapes here. Like I mentioned, there is high V and low V arch, as well as the buttressed segmental arch. Then there's a Gothic arch, shed rafter, utility arch, and parabolic arch. You can see images here, how that is applied in different types of buildings. So we are moving to the connections for glulam beams and arches. To produce the required framing in the cantilevered support, the beams are connected between supports. So one such connection is commonly used for this purpose when large beams are involved, designed so that the bolt is in tension with the plates, providing the required bearing perpendicular to the grain. To design the shape of cut so that the full depth of the beam is available for shear, um, you can draw lines at 60 degrees from the ends of both top and bottom plates. And then the horizontal cut should be the minimum length of bearing for the member size and placed at the center of the beam. Uh, Glulam arches. Arch connections are of two general types, upper hinge and lower hinge. So upper hinge connections may be made by gussets, bolts, or bolted plates. And a bolted connection is used for arches with a steep pitch with double shear plates at the center. Again, refer to the images. The bottom of lower hinge, the bottom or lower hinge of flight arches is generally one of the connections. Heavier arches may be connected at the base by any of the methods. Uh, and also, if the foundation is not so designed, the type of connection that is shown here, the bottom connection for light arches, please refer to the image, will be used, which includes a tie rod. So again, there are many images illustrating this concept, and we are moving to the next subsection, and that is parallel strand lumber. With large timbers now being at a premium, the wood industry is continually striving to expand the use of wood as a building material by investigating new methods and products that will use wood more effectively. Glulam timber sections made from smaller dimensioned lumber sections have been available for several decades and have been made in many different shapes and sizes. This development has provided sections that are larger, stronger, and more uniform in their physical properties than one of a section cut from a single large tree. So, two different approaches are currently being taken in the production of parallel strand sections. One is to use thin veneer panels covered with glue stacked so that the ends overlap in a staggered fashion and pressed to form a continuous slab or wood. And the resulting product is known as laminated veneer lumber. Um, So sections produced in this manner are denser, straighter, more uniform, and stronger than the original wood from which the veneers were cut. Again, refer to the images. Um, also, what else is important here? The other approach is to use random length of veneer strips, half-inch wide, that are aligned, coated with glue, pressed into a compact slab, and cooked with microwaves. And this results in denser, stronger, and more uniform element than the original tree. Please take a look at that here, and we are moving to the plywood structures. So plywood is recognized as one of the most versatile and widely used products in the building construction industry. We know that the plywood sheathing is manufactured by placing three or more wood piles or veneers with their grains at right angles to each other to produce a built-up section of some predetermined thicknesses. The piles are bonded together with waterproof glue that is set with heat and pressure. The result is a piece of material that is uniform in thickness and very strong in both directions. So standard plywood sheet size is 4 by 8 feet, and each type of plywood is available in various thicknesses, both in they're available in both in standard units and metric units. Thicknesses range from 5/16 of an inch to 1 1/4 inch, and that's 7.5 millimeters to 31.5 millimeters, either sanded or unsanded, and in various grades. Um, OSB, or oriented strand board, is commonly used in the place of plywood, typically as a less expensive alternative. OSB can carry the same or similar structural rating as plywood, and both are manufactured under APA, the Engineered Wood Association Standard PRP 108, a performance standard for structural use panels, and product standard PS1 and PS2. Box beams. In wood frame buildings in which long, deep beams are required, the weight of a solid glulam beam might be excessive, and a property design box may be substituted. This beam is made by sheathing a framework of sawn or glulam members on both sides with plywood, the thickness of which depends on the load to which the beam will be subjected. So please take a look at the images here. You can see how that is constructed. You can see plywood web beams as well, and that consists of one or more plywood webs to which sawn lumber or glulam timber flanges are attached along the top and bottom edges. So typical plywood web beam designs are illustrated here, and you can see box section, flange covered, box section, flange partially covered, I section, double I section, double box section, spaced beam, tapered beam, and beam top flange arched. Let's talk about stressed skin panels. A stressed skin panel consists of longitudinal framing members of wood covered in one or both sides by plywood skins. Again, refer to the images and the chart showing basic spacing of panel framing members, as well as some images illustrating the folded plate roof of stressed skin panels, as well as the curved panel for vaulted roof and plywood vaulted roof as well. And we are moving to the last little subsection of the chapter 10, and that's termite control for wood buildings. In some areas and climates, we know that wood that is in contact with or close to the ground is subject to attack by insects called termites. They bore into wood and, working from inside, may almost completely destroyed, leaving only an outer shell. Where wooden buildings or portions of them are subject to termite attack, protection against such infestation must be provided. Different methods of protection, both mechanical and chemical, have been tried with various degrees of success. Mechanical systems such as termite shields have proven to be ineffective. However, if used in conjunction with chemical treatment of the soil around the foundation, their use may be of some value. And you can see the picture showing the termite shields, how that is combined between the foundation and the joist. So there is a new method that appears to be quite promising, and that is trap, treat, release method. So once an insect problem is identified, a number of termites are trapped, treated with a surface toxicant, and then released to spread the toxicant throughout the colony. This method, combined with proper construction practices such as minimizing humidity levels in basement and crawl space areas, avoiding soil lumber contact, and burning or disposing all of the scrap lumber during construction will usually alleviate the problem. So this wraps up our chapter 10. Thank you so much for watching. I will see you in chapter 11.